All right, so new chapter, chapter 5. We skip over chapter 4. I don't even remember what chapter 4 is. Anyway, we don't try to cover chapter 4, at least not this year. So chapter 5, this is definitely part of any discrete structures or discrete math class, induction and recursion. And Professor Kanemoto and I are going to be splitting this chapter, so I'll do the beginning part and she'll do the later part. Doing some recursive stuff with the computer, so that'll probably come, I'm guessing, sometime next week. All right, but first we do mathematical induction, which is a proof technique. It's a really cool one, actually, and it's not that hard. And the idea is this. I remember the first time I saw this, I was kind of captivated by this. I was like, oh yeah, that makes a lot of sense. Except the analogy that I heard was about dominoes. All right. Your book's analogy is about a ladder. So this proof technique is used to prove that some statement is true for all integers. All right. For all integers n, thus and such is true. And one way to prove that something is true for all integers is to do the following two things. Show that it's true for the number 1, which is the first positive integer. Actually, I should, back that up and say we're trying to prove something is true for all positive integers. Show that it's true for the number 1, and then show that if it's true for any particular integer, let's say k, call it k, well then that implies that it's true for the integer k plus 1. So the argument kind of goes like this, for those of you who are into modeling these things using arguments. So one of the premises is p of 1. So we're trying to prove that the statement is true for all positive integers n. Prove that it's true for the integer 1. And then prove for all k, p of k implies p of k plus 1. And what mathematical induction says is that if those two things are true, then it will always follow that p of n is true for all integers n. Okay? And just in case you're wondering, there's really no special reason that we use k here and n here, other than that the thought is it makes it easier for people to follow. I remember once you get really, really, really comfortable with mathematical induction, you start to see people just using n here and also there. So the ladder analogy is this. If you want to convince somebody that you can reach any rung of this ladder, you could try to convince them of two things. Okay, first of all, I can reach the first rung. That's kind of important, right? And if I am at any particular rung of the ladder, say this one, well, then I can reach the next one. So it's kind of like the idea is, well, first of all, you have to be able to get on the ladder to begin with, right? And then maybe the thought of if I can get from any particular rung to the next rung, maybe that's just saying that the rungs are close enough together or something like that. So if you can convince somebody that they can get on the first rung of the ladder, and that whenever they're at any particular rung, they can get to the next rung, well, then that's enough to show that you can get to any rung of this ladder that you want. All right? Another way to look at it is, if you know that these two things are true, well, take p of 1 and put it in here. If you know this is true, well, then that means that p of 1 implies p of 2, and then p of 2 implies p of 3. And then p of 3 implies p of 4, etc., 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 right? And so that proves that your statement is true for all positive integers. Okay? All right. So let's do... Okay. So this is kind of what I just said. To prove that p of n is true for all positive integers n, where p of n is a propositional function, complete two steps. First, verify that p of 1 is true, and that's always really easy. All right, that's called the basis step, or the base case. Basis step. Okay. And then the inductive step is show that the conditional statement p of k implies p of k plus 1 is true. All right, so you start by assuming P of k is true. Show that P of k plus 1 then has to be true. Okay. All right, here it is. So there's a really cool story that goes along with this problem. And also, for any of you who took Calc 1, who have taken Math 4A, you have seen this formula. And maybe you've heard this story. So the story goes that the mathematician Gauss, who was a really, really famous mathematician in the, I want to say, 16 or 1700s. The story is that when he was in second grade, the teacher wanted to keep the class busy for a few minutes. I don't know, wanted to run to the bathroom or something. And so told the class to add the numbers 1 through 100, figuring that would keep them busy for a good 20 minutes or something. Well, after about 30 seconds, the teacher notices Gauss looking bored and counting the dots in the ceiling. And the teacher says, "Gauss, what are you doing? I gave you a problem to do." And Gauss says, "Oh, teacher, I'm already done." And so this is how Gauss did the problem. This is how he became Gauss. So the assignment was to add all the numbers 1 through 100. And so somehow Gauss, at the tender old age of 7 or something, realized that he could do it this way. So instead of going 1 plus 2 is 3, and 3 plus 3 is 6, and 6 plus 4 is 10, you know, the way that most of us would do it, Gauss said, okay, well, if I put the numbers 1 and 100 together, that makes 101. And if I put the numbers 2 and 99 together, that makes 101. And if I put the numbers 3 and 98 together, that makes 101. See where this is going? And how many pairs of those numbers are there? How many pairs? If there's 100 numbers. There's 50, right? So you have 50 pairs of numbers. They all add up to 101. Somehow in second grade, Gauss knew how to do 101 times 50. I don't think I learned that in second grade. And that comes out to 5,050, I think. Okay. And so that's an example, actually, of this formula. If you're trying to add the numbers 1 through n, now you have to worry a little bit about whether n is odd or even. All right, we're kind of assuming that it's even if we do it this way, but it doesn't have to be. That's one beautiful thing about this formula. So let's say instead of just going dot, 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 n, I go like this. So I'll put the last 3 in there like that. So if you pair 1 and n together, those are going to add up to n plus 1. And if you add 2 and n minus 1 together, those are also going to add up to n plus 1. And if you put 3 and n minus 2 together, those are going to add up to n plus 1. And if the number n is even, well, then you're going to have n over 2 pairs like that. So it's going to be n plus 1 times n over 2, which is exactly what that says, right? And it also works if n is odd, all right? And you can also prove this by mathematical induction. I know that when I teach Calc 1, I do not assume that my students know mathematical induction because probably most of them don't. So I have a different way of doing it. There's actually I was going to show this to you, and it went in with a bunch of other things I forgot about. If I remember, maybe I'll show it to you Thursday. It's what we call a proof by picture. You can draw a little diagram that will convince somebody that that is true. But we're going to prove it by mathematical induction. So here's how that looks. Okay. So remember, there are 2 steps to mathematical induction. There's the basis step, and then there's the inductive step. Okay. So when you're doing your proofs by induction, I would like you to label those 2 parts. And for the basis step, I think the easiest way to do it is just figure out what is the left-hand side. This is saying 10% battery. What is the left-hand side and what's the right-hand side? So the left-hand side is kind of weird. 1 plus 2 plus ... up to n. Okay, the basis step is n equals 1. So what do you think 1 plus 2 plus blah, blah, blah up to n should be when n is 1? What do you think that should be? It should be 1. It should definitely be 1. If it's saying 1 plus 2 plus blah, blah, blah up to n, and n is 1, that just means there's only one term. All right? The left-hand side is 1. And the right-hand side is 1 times 1 plus 1 over 2, and that also comes out to 1. Okay? So that completes the basis step, and now we do the inductive step. So the inductive step, again, is show that P of k implies P of k plus 1. Whoops. Okay. So assume the statement is true for some integer, some positive integer k. Remember this lazy way of saying k is a positive integer? I.e., we're assuming that 1 plus 2 plus blah, blah, blah up to k is equal to k times k plus 1 over 2. What we need to show is that the statement is true for k plus 1 so we need to show that 1 plus 2 plus blah, blah, blah up to k plus 1. Now here I have to be careful. How does this thing look when I replace n with k plus 1? All right, think of it like this. Blank times blank plus 1 over 2. If you drop a k plus 1 in there, one factor is going to be k plus 1. The other factor is going to be k plus 1 plus 1. So it would be k plus 1 times k plus 2 over 2. That's what we need to show. Does that kind of sort of make sense so far? So we showed the basis step. We showed that it's true when n equals 1. And now we're assuming that it's true for the number k. We're going to show it's true for the number k plus 1. And if we can do that, then we've shown it's true for all positive integers. Okay? All right. So just like with any proof, this takes a little bit of practice to really get the flow of it. It's not that hard. Okay? All right, so I'm going to say, I'm going to start talking about 1 plus 2 plus blah, blah, blah plus k plus 1. I want to show that that's equal to k plus 1, k plus 2 over 2. Okay. Well, here's what I can say. By what we call the inductive hypothesis, and I want to label that. The inductive hypothesis is the thing that we're assuming is true. And that would be this thing right here. This is called the inductive hypothesis. Okay. Since we're assuming that that's true, that means I can replace 1 plus 2 plus blah, blah, blah up to k with k times k plus 1 over 2. So we're using the inductive hypothesis right here. Okay. And don't forget there was an extra k plus 1 right there. All right, I want to show that that's equal to k plus 1 times k plus 2 over 2. All right, well now it starts to kind of look like a Math C problem. Just get a common denominator. Leave this as k plus 1 over 2. And now I would like this thing to be over 2. So I can add them together. So multiply on the top and the bottom by 2. Make sense? And now that those have the same denominator, you can add them together. This is all over 2. Upstairs you have k plus 1 plus 2, k plus 1. See where this is going? Pull the k plus 1 out of the top. And then your other factor is k plus 2. And what do you know? That's exactly what we were trying to show. So it's done. We showed that the statement is true when n equals 1. And we showed that the statement being true for n equals k implies that it's true for n equals k plus 1. And that's all it takes to show that 1 plus 2 plus blah, blah, blah up to n is equal to n plus 1 over 2 for all positive integers n. Done. That's mathematical induction. Okay. So what you start to notice about mathematical induction after a while is that at some point it turns into an algebra problem. It turned into an algebra problem right here. Right? We're just adding those expressions together. Okay. I read something really interesting about mathematical induction. I think it might have been in your book. And it said, the advantage of mathematical induction is that it's pretty easy to use. And it's what you use whenever you're trying to show that some statement is true for all positive integers. What it does a terrible job of doing is giving you any insight to why is the statement true. It really doesn't help with that at all. All right? I can very, very easily convince myself that that's true, but I have no idea why. All right? And that's why I really hope I'll remember between now and Thursday. I want to put together that proof by picture for you because I think that helps to see the why, at least for this one. Okay. The other thing about mathematical induction is, how did they ever come up with this formula? Once you have the formula, it's very easy to prove it. But how do you come up with it in the first place? Well, that probably goes in the category of why is the statement true? All right? So mathematical induction doesn't help you come up with the formula. It just helps you prove it. Okay? But actually, I just remembered that the next example, we're actually going to find the formula and then we're going to prove it. All right? So that's kind of fun. All right? But I don't want to just, rush into the next thing. I want you to take, as much time as you need. Well, for right now, take about a half a minute. Right? And take that in, wrap your head around it as best you can. I think I've said this to you before, but if I can get something to make 10% sense by the time you leave the room, sometimes that's the best I can do. And then I'll hope that the rest of it will come together. Maybe we'll do more examples next class, or maybe it'll come together when you do the homework. Okay? Not everything has to make 100% sense right as soon as I say it. All right? I remember saying that to a class once, and a couple of people looking really surprised. What do you mean it shouldn't make 100% sense? Okay. All right. While you're taking that in, I'm going to show you what the next example is. Actually, you know what I'll do? I never got around to adding the animations to these. I have to enable editing. Yep. I made this when I was first getting on the PowerPoint bandwagon, and so, like, look at this. I didn't even know how to not do both a bullet and a number. Get rid of the bullet, and that looks better. Get rid of the bullet. Get rid of the bullet. Okay. Any questions on number 1? Example 1. Okay. All right, there it is. So just part A. Okay, here it is. This is what I was talking about. Find a formula for that expression by examining the values of the expression for small values of n. I feel like this is something that you might be able to get a head start on. All right. Maybe you don't need a lot of help from me to do this part. Let's see. Well, we want to stay out of there because the podium blocks that. Or did we move the podium? Can you guys see down here now? Can I write here? Can you see that? Oh, I can use that part. Excellent. I just want to stay away from here. Okay. So let's start thinking about what could the formula be for 1 over 1 times 2 plus 1 over 2 times 3 plus blah, 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 blah. Okay? And it's by examining small values of n. So I'll get you started. When n equals 1, need to start there. 1 over 1 times 2, 1 over 2 times 3, up to 1 over n plus 1. Okay, well, n equals 1, that's really easy. That just means it's only the first term. So that would be 1/2. Right? When n equals 2, it's the first 2 terms. It's 1/2 plus 1/6, which adds up to 1 over, or what does that add up to? Three six plus 1/6, 4/6, otherwise known as 2/3, right? So do the next couple. I bet you'll see the pattern. Take about a minute. So we're going to form a conjecture, a mathematical guess, what that adds up to in terms of n. No, it doesn't. Right? There's no equal sign. No equal sign. Yeah, it kind of looks like this is the answer, right? But it's not. It's saying this plus this, blah, 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 up to this equals what? And I'll make space to do the proof. So another 25 seconds, and I want to know what is it when n is 3 and what is it when n is 4. Did you get it for 3? What did it come out to? Did anybody else get 3/4? 3/4, 3/4, 3/4? Yep, I bet it's 3/4. Notice you can do a little shortcut with this. You don't have, like when you get to n equals 4, you don't actually have to add 4 fractions together. The first, all but the last fraction is gonna just be the answer from the previous step, right? So this is 2/3. I could have just done 2/3 plus 1/12. And in the next one, I can just do 3/4 plus the next one, which would be 1/4 times 5. And that comes out to 13/17. What does it come out to? 16/20, which is 4/5. See the pattern? 1/2, 2/3, 3/4, 4/5. So what's it going to be for n, do you think? N over n plus 1. Excellent. Okay. So the conjecture, just a guess at this point, we'll call it a claim, is that 1/1 times 2 plus 1/2 times 3 plus blah, 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 up to 1/n plus 1 is equal to n over n plus 1 for all positive integers n. That's what we think is true. So let's try to prove it. Start with the basis step. See if you can do the basis step. Basis step's usually easy. Show that the left side equals the right side when n equals 1. Well, when n equals 1, the left side is just the first term of that thing, 1/1 times 2, which is 1/2. And the right side that we just discovered, that they didn't give us, n over n plus 1, that's 1/1 plus 1, isn't it? Which is also 1/2. Woohoo! All right. Basis step out of the way. Okay, so now the inductive step. This is always the longer part. Suppose 1/1 times 2 plus 1/2 times 3 plus blah, 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 up to 1/k, k plus 1, is equal to k over k plus 1 for some positive integer k. And remember, that statement is called the inductive hypothesis. right? Suppose that's true. What we have to show is that 1 over 1 times 2 plus 1 over 2 times 3 plus blah, 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 blah plus 1 over k plus 1 plus the k plus first term, which is 1 over k plus 1, k plus 2. Okay? That's what the left-hand side comes out to when n is k plus 1. We have to show that that's equal to k plus 1 over k plus 2. That's what we have to show. Okie dokie. So it kind of goes the same way as it did before. Start with your left-hand side. And the reason that I always like to include the k term when I write it out at this point is because in the next step you're going to replace all the terms up to k using the inductive hypothesis. So take that, take this, just those first k terms, and replace them with k over k plus 1. So that's where we're using the inductive hypothesis. By inductive hypothesis, IH. I see another Math C problem coming. I think I can finish it in this spot. Okay, so we have k over k plus 1 plus 1 over k plus 1, k plus 2. Need a common denominator, which would be k plus 2. So that's going to be, on the bottom, k plus 1, k plus 2. On top, it's going to be k plus 2 plus 1. See where this is going? K times k plus 2 is k squared plus 2k plus 1. And that's over k plus 1, k plus 2. So what can I do with that? What do I need to do with that? Factor. I need to factor on top. Oh, k squared plus 2k plus 1. Isn't that k plus 1 squared? Oh, look what happens. Get rid of one of the k plus 1s. And I think that's exactly what we were looking for. That comes out to k plus 1 over k plus 2. Yeah?
Can you mark us down if you didn't say k value for or is that assumed?
You don't need to say that because it's assumed because we're proving it for positive integers. So yeah, we don't have to worry about k being negative 1. It's a good thought though. Need to look out for that kind of stuff sometimes. Okay. So there it is. It's proven. Therefore, 1 over 1 times 2 plus 1 over 2 times 3, da 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 da, up to n, 1 over nm plus 1 is equal to n over m plus 1 for all positive integers n. And that's mathematical induction. Seems doable, doesn't it?
So we're proving that using that.
As opposed to proving math using biology? I think I kind of know what you're saying. But it shouldn't feel like you're using what you're trying to prove, because we're not. For me, the magic of mathematical induction really happens, well, starting here. All right, it's using your inductive hypothesis and transforming this thing into k plus 1 over k plus 2. That's where it really kind of comes together for me. That's where the magic happens. Okay, so you will find that for all of these where you're proving that two things are equal, any kind of summation formula, which is what the last couple have been, those are always going to involve a little bit of algebra. Okay? And it usually won't be difficult algebra. Sometimes it'll be sort of annoying algebra, but it won't be difficult. Where it gets a little more difficult, believe it or not. Okay, so we did part B. Part B is just to prove it. Already did that. Okay. This is a little more difficult, proving an inequality using mathematical induction. Okay. And I think I can get you to understand why this is a little more difficult. Let's see, I don't want to get rid of anything if people are still thinking or writing or looking or... Okay, so look at what we're trying to prove next. We're trying to prove that 3 to the n is less than n factorial if n is an integer greater than 6. So that's one thing that's different is we're not this time we're not trying to prove a statement's true for all positive integers, just for positive integers starting with, it would actually be starting with 7, right? Do you know about n factorial? You probably do. Okay. And probably every math instructor on the planet has the same joke about this when we first bring it up. The way to read that is not n! You could read it like that if you wanted to, but most people read it as n factorial.
Sorry, I missed that last part. You blew up my radio.
You want me to say it louder? No. Okay. N factorial, which means take the number n and multiply it by every smaller integer all the way down to 1. I think this is a favorite example in computer science. Lots of stuff you can do with that in computer science. Okay, so for example, 1 factorial is just 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. And what a lot of people are surprised when I tell them, by definition, 0 factorial is defined to be 1. All right, this definition here doesn't do you any good if n is 0. But it is helpful to have a definition of 0 factorial, and we define it to be 1. And I have a favorite, what's the word I want? A favorite argument for why 0 factorial should be 1. All right, other than just because I said so. I mean, just because I said so is a good enough reason. I mean, that's kind of what by definition means. All right, but when we get to counting, I'll come back to 0 factorial. The biggest reason to make 0 factorial equal 1 is because it makes a lot of formulas work that wouldn't work if we didn't have that. Okay. So we want to prove that 3 to the n is less than n factorial for n greater than or equal to 7. And I'm saying it like that because I want it to be clear to everybody why when I go to do the basis step is going to be n equals 7. All right? We're not trying to prove it's true when n equals 6. I don't even know if it's true when n equals 6. I'm guessing it isn't. If somebody has a calculator handy, I could use your help. What is 3 to the 7th? 2187. And what is 7 factorial? 5040. Okay, I'm totally convinced it's true when n equals 7. $21.87 is less than 50.40. So that checks out. Okay, now the inductive step. Suppose that 3 to the k is less than k factorial for some k greater than or equal to 7. We need to show that 3 to the power k plus 1 is less than k plus 1 factorial. Okie dokie. All right. I'm going to make a little disclaimer right now. I have not thought about this problem since probably about this time last year. Okay. It would probably be a good idea for me to look at these again because I don't know how to do all of these right off the top of my head. Sometimes I have to think about them for a little bit. I think I can make this one come together. Let's see. So I think what we want to do is start with 3 to the k plus 1. All right, and using a string of equal signs and less than signs, eventually get to k plus 1 factorial. Okay? So I think what I want to do is this. Okay. 3 to the k plus 1 is equal to 3 times 3 to the k, isn't it? Right? Using property of exponents, 3 to the first times 3 to the k, add the exponents, right? And now, by the inductive hypothesis, we know that 3 to the k is less than k factorial. So I think if we put a less than sign here, we can say that 3 times 3 to the k is less than 3 times k factorial. We eventually want to get to k plus 1 factorial. All right? Now, k plus 1 factorial, I don't know how many of you took Math 4B. That might have been a useful question for me to ask at some point. How many of you have taken 4A? How many of you have taken 4B? All right. You learn to really get good at manipulating factorials in Math 4B when we get to the sequences and series chapter, which my 4B class is not in yet. All right. Okay. So I just want to point out to you off to the side here somewhere that k plus 1 factorial, what does that mean? It means start with the number k plus 1 and multiply by every smaller number until you get to 1, right? Well, what is k times every smaller number until you get to 1? What's that called? That's called k factorial. So what I'm trying to tell you is that oftentimes when you're working with k plus 1 factorial, it's really helpful to write it as k plus 1 times k factorial. Okay. All right. So since I'm trying to get to k plus 1 factorial, and I may have to pretty this up at the end. This is kind of like doing a maze by cheating and starting at the finish spot and trying to work backwards, or go part of the way from start and part of the way from finish and meet somewhere in the middle. All right. In math, that's not really cheating, as long as you are good at hiding the fact that you did that at the end. I have this great quote about doing math that I need to dig up for you. 3 times k factorial. I'm trying to get to k plus 1 factorial, which I know is k plus 1 times k factorial. Oh, okay. So all I need to do is figure out what's a relationship between 3 times k factorial and k plus 1 times k factorial. Well, I think the relationship is that 3 times k factorial is less than k plus 1 times k factorial. And that's because, remember, k is not just any old number. It's something that's at least equal to 7. It's greater than or equal to 7. Okay. K plus 1 is greater than or equal to 3 as long as k is greater than or equal to 2, right? So we're actually, k greater than or equal to 7 is a lot more than we need, but we have that. Okay. So this is how it goes. You start with 3 to the k plus 1, write that as 3 times 3 to the k. By the inductive hypothesis, that is less than 3 times k factorial. Okay. And this is where I would not expect anybody, I don't even think this way, to immediately come up with this as the next step. I came up with that by working backwards from what I'm trying to get to. Okay. But now I'm going to pretty it up so it doesn't look like I cheated. 3 times k factorial is less than k plus 1 times k factorial. And that's because k is greater than or equal to 7. And k plus 1 times k factorial is exactly equal to k plus 1 factorial. That does it. All right. So if you follow the string of equal signs and less than signs, we have that 3 to the k plus 1 is less than k plus 1 factorial, which is exactly what we're trying to show. And therefore, three to the n is less than n factorial for all n greater than or equal to 7. Dun, 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 dun. All right. So the inequalities are more difficult than the equations, and I think you start to sort of see why they're more difficult here. You have this wiggle room where you can say something is less than something, and that requires you to think outside the box a little bit. It's easier, it's actually much easier to talk about something that's equal to this. You just do some algebra and rewrite it. You got to think outside the box to come up with something that's bigger, and that will be helpful. Okay? All right. Any questions whatsoever? We are a little overdue for a break. Is that the end of 5.1? It's not. Oh, good. Okay. So this would be a great thing to look at during the break. Try to find where they cheated in this proof. All right? So they're trying to say that for every positive integer n, the sum of I going from 1 to n, and in case you're not familiar with that notation, the sum of I going from I equals 1 to n is just a short, geeky way of writing one plus 2 plus blah, blah, blah up to n. And this supposedly proves that that is always equal to n plus 1/2 squared divided by 2. Okay. It's worth taking a minute to convince yourself, first of all, that that's not true. That can't possibly be true. All right? And I want you to think about why. But then look at this fake proof and try to find where they cheated. All right? So do that during the break. We'll take about, I don't know, 7 minutes. There we go. 5.2. We're just going to do strong induction. Strong induction. So you're going to see the difference between ordinary old mathematical induction and strong induction. It turns out, interestingly enough, that they are logically equivalent. It's just that in some problems, one of them is much, much, much easier to use than the other one. Okay. All right. So here is regular mathematical induction. This is what we just went over. To prove that a statement is true for all positive integers, first show it's true for n equals 1, and then show that P of k implies P of k plus 1 is true. Okay? Strong induction does this. Instead of just assuming P of k in the inductive step, you assume that P of 1, P of 2, all the way up to P of k are all true. All right? And then show that all of those together imply that P of k plus 1 is true. Okay? So we probably, if I remember correctly, I did not assign as much homework from this section as from 5.1. So we'll do more regular mathematical induction than strong induction. Okay, so here's the difference. Mathematical induction, you show that P of k implies P of k plus 1. Strong induction, you show that P of 1 through P of k, all of those together imply P of k plus 1. Okay? All right. So, first example, use strong induction to show that all dominoes fall in an infinite arrangement of dominoes if. All right, so the domino analogy is just like the ladder analogy. Okay? So here's what you know. You know that the first 3 dominoes fall, and whenever one domino falls, the domino 3 further down the line falls. All right? So, in other words, you know this. We know, all right, so make the statement P of n be the nth domino falls. We know P of 1, P of 2, and P of 3 are all true. And we know that P of k implies P of k plus 3. Okay? All right. Let me think about this for a second. So the basis step well, the way they set it up there was the basis step is still P of 1, so that's given. Okay, it's given that the first domino falls. It was actually given that the first three all fall. Okay. So the inductive step is going to say, suppose that the first k dominoes fall where k is at least I think we can say at least 3. Oh, okay, I got it. There were some little light cobwebs up there. I think they're gone now. Told you this happens sometimes. Okay. So we must show, see if I can get a better pen here. La-da-dee-da-da-da-da-da. Is that my only black pen? Oh, no, you know what? I had to grab extra pens yesterday because I had forgotten my stash. Here we go. This one should be good. Okay, we must show that P of k plus 1 is true, which means the k plus first domino falls. Okay, so remember the other thing that we know. We know P of 1, P of 2, and P of 3 are all true. And we know that whenever P of k is true, it implies that P of k plus 3 is true. Okay? So what I'm going to do is work backwards. I want to show that P of k plus 1 is true. I know that P of k implies P of k plus 3. So what would imply P of k plus 1? P of k, and go the other way. Remember, the k plus 1 is over here. Minus 2, right? Well, I think we actually know something about P of k minus 2. Since, let me see. I might want to, well, okay. We're assuming that the first k dominoes fall from 1 through k, where k is at least 3. Since P of 1 through P of k are true, where k is at least 3, we know that P of k minus 2 is true. And where we're using the fact that k is greater than or equal to 3, if we didn't know k was greater than or equal to 3, there would be no such thing as P of k minus 2, right? Because this guarantees that k minus 2 is at least 1. In other words, it makes sense. I should say is true. Okay. Well, by the inductive hypothesis, P of k minus 2 implies P of 3 more than that, right? That's what this says right here. And that's exactly what we wanted. means P of k plus 1 is true. And that's what we wanted to prove. So this kind of sort of, it's kind of a silly example in terms of, there's really not any math in it. But what it does a good job of doing is you kind of start to see when do you use strong induction instead of regular old induction. All right. Use strong induction whenever there's sort of a gap between your cases is not the right word, between your statements, all right? Like in this case, there's a gap of 3 between P of k and P of k plus 3, okay? So you fill in that gap with, the trade-off is that you have to know more things are true at the beginning, okay? And I think we're coming up to an example here where we will actually show those things are true, and then we'll use strong induction. After you show those individual cases at the beginning, the strong induction ends up being a lot easier than the mathematical induction. Okay. So let me show you what's next. And you'll still get some time to take that in. Okay. Classic kind of problem to practice strong induction. So using just 3-cent and 10-cent stamps, we want to figure out what amounts of postage can you make out of 3-cent and 10-cent stamps. Okay. So while some of you are thinking about example 1, so I'm going to leave it up here for a minute. While some of you are thinking about example 1, if you're happy with example 1, you think you kind of sort of got it, start thinking about just letter A. So letter A, I don't really have to tell you anything. Just start writing down numbers. I'll show you what I mean here. So for example, the smallest amount of postage that you can make with 3-cent and 10-cent stamps is 3 cents. Right? Use 1 3-cent stamp. The next amount of postage you can make with just 3-cent and 10-cent stamps is 6 cents, right? And then you can do 9 cents, and then you can do 10 cents, right? Because you have 10-cent stamps. See what I'm doing? At some point, you will get to an amount where starting from that amount on, you can form any amount you want. All right, but it doesn't happen right at the beginning, right? Like you can't do 4 cents, you can't do 8 cents. Can you do 11 cents? I don't think you can. What's the next amount you could do? You could do 12. Can you do 13? Sure, a 10 and a 3, right? Can you do 14? No. If you have a 10-cent stamp, you can't get 4 cents. And if you don't have a 10-cent stamp, well, you can't. 3 doesn't go into 14, right? So the next one would be 15, which is 5 times 3 cents, right? Can you do 16? You can do 16, right? 10 plus 3 plus 3. Can you do 17? You can't do 17. Ah. Okay, you can do 16, you cannot do 17, you can do 18, and you can do 19, right? And you can do 20. I think about this for a few more seconds, but I think starting at 18, you can make any amount 18 or bigger, I think. Is that right? You can do 18, you can do 19, 20, 21. Can you do 22?
4 3 cents.
Ah, very good. That one actually had me stumped for a second. Yeah, you can do 22 as 4 3-cent stamps. and a 10-cent stamp, right? And then 23 is 2 10s and a 3. So I think starting at 18, you can make any amount using 3-cent and 10-cent stamps. Okay, so I don't know what prompted me to do this, because I don't usually do this, but I'm glad I did. I actually have the solution all written out on the next slide for letter B. So let's take a look at it. So the claim is, I guess this would go under letter A, you can form any amount n cents using 3-cent and 10-cent stamps for all n greater than or equal to 18. You know, I kind of feel like you might get a little bit more out of this if I actually write out the solution to letter B than just looking at it on the slide. Let me do that. Let me write it out and then I'll compare it to what it says on the slide. Okay. Let me see. Letter C, I might not try to do that. Letter C, we might just be able to get it off the slide. Okay. So proof. This is by mathematical induction, regular old mathematical induction. So first the basis step. Show it's true for 18. Well, that's easy. 18 cents can be formed with 6 3-cent stamps, right? That's the basis step. So the inductive step goes like this. Assume you can form K cents, where K is at least 18. Show that you can form K plus 1 cents. Okay. So the way that you get from K to K plus 1 in any of these stamp or money problems is you show, okay, I have K cents of stamps in front of me. By exchanging some of the stamps for other stamps, how can I make my stamp collection be worth 1 cent more? All right? And this always with mathematical induction, not with strong induction, but with mathematical induction, this is by cases. Okay? All right. If you have 3 3-cent stamps, if you have that, then the way to get from K to K plus 1, the way to increase the value of your stamp collection by 1 cent is to trade them for 1 10-cent stamp. I'm not talking about like making a fair trade, all right? See that? So you're trading 9 cents for 10 cents. And you can see an example of that, like going from 19 to 20. 19 was a 10-cent stamp and 3 3-cent stamps. 20 is just 10 and 10, right? So they gave up the 3 3-cent stamps and picked up a 10-cent stamp. Okay? So that's what you do if you have 3 3-cent stamps. Now what if you don't? If you don't have 3 3-cent stamps, and you might not, well, then I claim that you must have, because remember, you promised me your stamp collection was worth at least 18 cents. If your stamp collection is worth at least 18 cents and you don't have 3 3-cent stamps, then you must have at least how many 10-cent stamps? At least that many. Right, I was just about to say, the temptation is to say 1, right? Because we know we have at least 18 cents worth. So if I don't have at least 3 3-cent stamps, then that means I have at most 2, which is worth 6 cents. Well, if I only have 1 10-cent stamp, then my stamp collection might only be worth 16 cents. So if I know for a fact that my stamp collection is worth at least 18 cents, and I don't have 3 3-cent stamps, then that must mean that I have at least 2 10-cent stamps. So what can you do with your 2 10-cent stamps? So I should turn in my 2 10-cent stamps for how many 3-cent stamps? Not 6. That's taking us the wrong way, right? 6 is worth 18 cents. We're trying to make 20 into 21. Trade them for 7 3-cent stamps. See how that works? I think these are kind of cool. So you're making the value of your stamp collection go up by 1 cent. The way to do that, if you have 3 3-cent stamps, trade them for 1 10-cent stamp, makes it go up 1. Well, if you don't have at least 3 3-cent stamps, then you must have 2 10-cent stamps. That's where we're using that K is at least 18. And then trade those 2 10-cent stamps for 7 3-cent stamps. Okay? So those 2 sentences there show that if you have K cents, you can always make it into K plus 1 cents. P of K implies P of K plus 1. And that proves it. Does that kind of sort of make sense? It's kind of cool. It feels a little like a puzzle. Okay. So the last thing I want to do with you today is show you what this proof looks like if you use strong induction. Strong induction is a little bit more work at the beginning, but it's work that you kind of have to do anyway. And then it's less work during the inductive part. And I think I'll just bring that up on here. Oh, let me see. Oh, okay. That's pretty similar to what I said, right? I just switched up the order of the 2 cases. Right? Remember, WMS stands for we must show. That's me being lazy. Yeah? Yeah, especially in a problem like this. So it's not that. Yeah, this one's not as much. This one doesn't feel as much like proving math using math, right? It's a little math, but not as much. This one's normal. All right. Oh, I see. This one is actually kind of substantially different to how I wrote it up there. I'm kind of glad I did it that way. So I started by assuming that you had, or suppose you have 2 10-cent stamps. If you do, trade them for 7 3-cent stamps. If you only have one 10-cent stamp, or at most one, then you must have at least 3 3-cent stamps, because otherwise your stamp collection is not worth at least 18 cents, right? You could have one 10-cent stamp and 2 3-cent stamps, and that's only worth 16 cents. All right, good stuff. So here's how it looks different using strong induction. I wish I had this animated. Okay. So the first thing we're going to do is show that P of 18, P of 19, and P of 20 are all true. All right. So 18 cents is 6 3-cent stamps. 19 cents is a 10-cent and 3 3-cent stamps. And 20 cents is 2 10-cent stamps. Okay. Now, the notation for strong induction takes a little getting used to. All right. And I think I have, let me just peek at something here. Oh my gosh. I'm going to try to dig up another example of strong induction for next time. I don't feel like this is enough. All right, so the inductive hypothesis is that P of J is true. The notation really starts to get annoying with strong induction. For all j between 18 and some mystery number k. So remember, let me break this down for you, a little simpler. The notation is just terrible. What this is saying is, starting with 18, P of 18, P of 19, all the way up to some mystery P of k are all true. This sentence right here, don't even need all of that. P of j is true for j between 18 and k. That says the same thing as what I wrote over there. P of 18, P of 19, all the way up to P of k are all true. K has to be at least 20. And we can assume that k is at least 20 because we already knocked out the cases 18, 19, and 20. Okay? So we have to show that all of those cases together imply P of k plus 1. And here's how that works. Using the inductive hypothesis, we know that P of k minus 2, so this is a little bit like the domino example, right? We know that P of k minus 2 is true because k minus 2 is greater than or equal to 18. So in other words, k is at least 20, and that means k minus 2 is at least 18. So we know P of k minus 2 is true. And now I'm going to jump from k minus 2 all the way to k plus 1. So if I have k minus 2 cents worth of stamps, and I want to get to k plus 1 cents worth, what can I do to get from k minus 2 to k plus 1 in terms of stamps? Add 1 3-cent stamp. To get from P of k minus 2 to P of k plus 1, add a 3-cent stamp. See? So by nailing out more cases in the beginning, you can skip over that. You can skip over this right here. All right? If you have the 3 3-cent stamps, do this. And if you don't have the 3 3-cent stamps, do this other thing. You don't have to say all that with strong induction. Just say to get from P of k minus 2 to P of k plus 1, just add 1 3-cent stamp. So it's kind of like this. Starting with 18. 18 is 6 times 3. 19 is 10 plus 3 times 3. 20 is 10 plus 10, or I could just say 2 times 10. So now to get to 21, I'm going to write that up here. because I want to show you the relationship between 18 and 21. 21 is just one additional 3-cent stamp. 22 is just one additional 3-cent stamp from this. It's the 10 plus the 4 times 3. And then 23 is one more 3-cent stamp than 20 was. And you can keep that going as long as you want. Okay? Because we nailed out the three base cases in the beginning, 18, 19, and 20. That kind of sort of makes sense, at least 10%. I think it would be a really good idea to have another strong induction example for next time. So I'll try to dig one up. I can hardly believe I only have one. Well, I have two, I guess, technically. I think we could use one more. Okay. So, but that's all I have for now. Okay. So one more strong induction example coming. First thing Thursday.